The second day of section 8.2 will be spent practicing half-angle formulas and all of the other formulas that we know so far inside of identities. If we were asked to find the sine of 165 degrees, it wouldn't be very easy to do using what we know from unit circle, because 165 degrees puts us right about here, and the reference angle for that situation is 15 degrees. Well, we don't have coordinates for a 15-degree angle memorized on a unit circle. But if we realize that 165 doubled is 330, we can use our half-angle formulas and find the sine of 330 divided by 2. 330 divided by 2 is 165, but the half-angle formula for sine says plus or minus the square root of 1 minus cosine theta, all divided by 2. So even though we're using 165 as our question, if I double it and get 330, that's the angle that goes inside theta right there. And double 165, which is 330, puts us all the way around the unit circle and just 30 degrees short of a full trip around the circle, and a 30-degree reference angle we can do. We know that at 30 degrees on a unit circle, the x-coordinate is long, root 3 over 2. The y-coordinate is short and negative, negative 1/2. So, to finish our problem, plus or minus the square root of 1 minus cosine of 330, all divided by 2. The diagram right here, we just found out that the cosine of 330 is root 3 over 2, so we get as an answer plus or minus 1 minus root 3 over 2, all divided by 2. And while that's a pretty good answer, there's some simplifying in here that needs to be done. The first issue is that we have a fraction inside of a fraction, so I think if we do multiplying the top and the bottom by a half, it will help eliminate this fraction down here. So the new smaller version is plus or minus the square root 1/2 minus root 3 over 4. And so while the 1/2 cancels the big denominator right here, 1/2 distributed to both terms in the big numerator is 1/2 and a negative root 3 over 4. I can combine those two together by finding a common denominator. 1/2 is the same thing as 2/4, so 2 minus root 3 over 4. And then the final piece of simplification is the fact that the square root of the denominator can be easily done. The square root of 4 is obviously 2, plus or minus big square root for 2 minus root 3, but then the denominator is no longer underneath the square root and we just get a 2. And then the final part to figure out is whether we should take the positive or the negative version. Going back to the original question, the sine of 165 degrees puts us in quadrant 2. Quadrant 2 has negative x values, positive y values. Since sine is looking for the y coordinate, the negative answer doesn't make sense, and our final overall answer is just the positive 2 minus root 3, all divided by 2. So again, if you can't evaluate directly a certain angle on the unit circle because the reference angle is too small, try doubling and using the half-angle formula. And then the final part of 8.2 is going to be using all of our double and addition formulas in identities. Normally we would say work on the more complicated side, and in this example the right side looks more complicated. But on the left side, sine 3 theta also presents some challenges because we don't have a triple angle formula. So if we work on the left side and change sine 3 theta into the sine of 2 theta plus theta, instead of looking for a triple angle formula, we can use the sine addition formula. And we should know that sine addition is sine cosine plus cosine sine. And instead of s's and t's, we have 2 theta for the first argument in both cases, and theta as the second argument in both cases, the argument in the second part. So while we haven't quite reached the right side yet, we now know that sine 2 theta can be simplified into something else, and so can cosine 2 theta. Sine 2 theta is known as 2 sine theta cosine theta, and I still have my second cosine theta right here. Cosine 2 theta is known as cosine squared theta minus sine squared theta. And if I distribute, well, I won't be distributing in the first term, but I have to distribute the sine theta to both of these in the second term. The first multiplied out becomes 2 sine theta cosine squared theta, and that's promising because our final answer has sine theta cosine squared theta. And the second one, when I distribute the sine theta to both of these, produces sine theta cosine squared theta minus sine cubed theta. And now we're one step away from finishing. This and this are like terms producing 3 sine theta cosine squared theta. The last thing is minus sine cubed theta, and that's exactly what we were attempting to prove. Okay? So again, with these new identities, because we have addition formulas and subtraction formulas and half angle formulas and double angle formulas, try working with the shorter side maybe and expanding out, and after you do all your algebraic simplification, you wind up with what you were looking for. Okay, that's all.